So our next speaker is Nathan Srebro, who's a professor at the Toyota Technological Institute with cross appointments in the University of Chicago. He was previously a faculty at Technion, and he did his postdoc at MIT. I mean, I don't have to make the list of all the main achievements. You were a postdoc? No, you PhD is a bit over. Yeah. This morning I'm a bit yeah.
Postdoc in Toronto.
Yeah, postdoc in Toronto. Yeah. So Nati is a very good friend of UW. He's visiting very often, and looking forward to your latest research.
Thank you. Thanks, Aidan. Thanks for inviting me. It's always great to be here. So I'm going to be talking about some work on autoregressive models and language generation, and this is based on two papers. One is a purely theoretical paper with a bunch of authors, but mostly I want to highlight Nirmit, who really is the student that did all the work here, and the other is a mostly empirical paper, again with several co-authors, but mostly Shen Shao, who really put this project together and did the work. So as I mentioned, one is purely theoretical, and we'll really try to define the basis for theory for how to understanding this autoregressive chain of thought process that I'll define in a second. And we'll see that our main kind of motivation in doing that, and what we'll see is that will directly lead to motivating kind of rediscovering or like leading to attention of like why attention is very natural. And then these two parts are still just theory and revisiting existing things. We'll see that once we understand things this way, it will naturally lead to another modification to the autoregressive process that I'll mention at the end with the very nice empirical benefits. And throughout, we'll go through these people. I'm curious, how many people recognize all three of these? 2 out of 3? Yeah, okay. So we'll visit the third one. You'll get to know the third one as well. Okay, so great. So chain of thought, just I'm sure all of you have seen this before, but we have processes that generate one token at a time. And the thing is that if we just have a question and we immediately want to generate the answer, that can be very difficult for machines, also for you guys. But if we have the question and then we kind of like generate a bunch of tokens that kind of think through the process, then we can get the right answer. And we can get that on questions like this, or even more complicated questions that really, I mean, I don't think any of you can answer. I mean, it doesn't really matter what the details here. I mean, you can hopefully quickly convince if you can like answer this in one shot. You really need this chain of thought. So let's formalize what we have here. Assuming everybody has seen chain of thought before, but let's try to formalize it. So what we have in the chain of thought process, the important thing is we have a generator, a next token generator. So this is our base generator. So what it does is it just takes a string and generates one token, the next token. And the way we're using it, we're feeding the input to it, and we're each time applying it iteratively. And we're applying our function and then appending the result. Okay, so then applying it again and appending, and applying and appending, and applying and appending. So formally, each time, we define the output after t steps, so initially it's just the input, and after t plus 1 steps, we take the input after t steps and append to it, applying the function on that input. Okay, is this clear? Okay, this is, yes, Sue?
Is HCOT deterministic or?
Yeah, so here we're taking everything, good question. So here we're taking everything to be deterministic. You can think of H as maybe like randomized, and then this whole thing is randomized. Right now, just for this entire talk, think of H as deterministic. Okay, so H, for any function H, I can define the COT. So the COT is the mapping from the input to this entire string, which I'll call the chain of thought. But really what we care about the answer, and we're going to think of the answer as what comes at the end, and formally just the last token, okay, so the last bit. And so in particular, we can also, for any base generator H, we can also think of the corresponding end-to-end function it implies, and this is just a function from the input to the very last bit. Okay, so again, it's just a function from a string to a single token, okay, but it's not just applying the function once, it's applying the function multiple times. And given a base class of predictors, so you can think of it, for example, the class of all transformers. You can ask, what can I do with transformers? Really, what you want to ask is not what I can do with transformers in terms of taking, if I think of the transformer as a sequence to token function, it's not really what I can do with applying it once, but really what I want is I have this class of, base class of generators, say transformers with different parameters, and the actual classes I care about are this chain of thought class, the class of all mappings from input to the chain of thought, and even more importantly, this end-to-end class, the class of all mappings that I can get by taking any transformer and mapping it. And crucial in all of this is we're applying the same function over and over again, the same h, right? If you think of it in terms of a transformer, you choose, it's not that for each step you use a different parameter setting for the transformer. You choose parameters, right? That determines which, your class of transformers, this base class, script h is transformers you can get with all different parameter settings. You choose a single parameter setting for the transformer, right? You set the weights, and you now fix the weights, and you use the same weights, the same generator h to generate each step here. So this process is time invariant, which is going to be crucial for us. Okay, and now we understand this, we can ask questions about how well can we learn this, okay? And so we'll define learning here in two different settings. One is the standard kind of pack notion of learning. I have a function from inputs to outputs, or input, the inputs here to my answer here. You give me a bunch of examples of input and answer, and I need to find learn the mapping between them. And again, I'm going to do that. I'm going to learn the generator, so I'm going to assume that there is some generator in my class that implements this end-to-end mapping, and I want to learn it. Yes, question, Kevin?
I have a very naive question.
Yeah.
Is there anything special about chain of thought here, or is it just an autoregressive model? Like, what makes this? What does chain of thought add on top of autoregressive?
So to me, chain of thought means you take this autoregressive process and you look at you apply it for many steps, and then you look only at the last thing. That's what I define as chain of thought. Okay, so does that answer your question? Okay. So maybe if you want to get like pedantic definitions, maybe I would think of autoregressive in general when you have like, there's nothing special but just the last answer, the input, the last answer, you have like something that goes on all the time. And for me, really, what I have is really just a mapping from an input to an answer. Like, what's the square root of 7,329? And the answer is, I don't know what the answer is, okay? But the way you answer that is with this autoregressive process. That, okay? Yeah.
Just another really dumb question. So H takes variable length inputs.
That's true.
And so I wanted to clarify what you meant by time invariant, because somehow it might do something different for a longer context.
Right, so Rob wants to cheat, and he's allowed to based on my definitions. Okay, so what Rob points out, then you can like resolve in various ways, is that since I'm saying time invariant to the same things any step, but actually the input it's a function from a string to an output. That's very well defined, okay? And you could define these functions in a way that the first thing they do is they look at the length of the string, and then they branch based on a whole bunch of different things, okay? But we're not interested in functions that cheat like that. And in particular, the important thing for me is once I give you the class H, the hypothesis of class H, it's not going to include functions that cheat in that way. So you're only going to choose a single function from it. The important thing is you choose a single function to use over and over again, and this should be like it's going to be, you'll see a simple function. Like for example, if I limit you to be a transformer, okay, so a transformer is, you can think of it as a variable length input to output function. You choose a single setting of parameters. Is that?
So, I mean, I'm not sure I fully understand, but somehow how it processes the most recent token doesn't matter on how many.
So I have to define a function from a string to the next token. I can define, there's a bunch of functions like that. I mean, we'll see some example. One, maybe the most obvious example you should have in your head is a transformer. So a transformer with a fixed, that's I think what's kind of one of the very important things of a transformer. It is a function from a variable length string to, at least the way we use it, to the next token. So with the same parameters, it can take strings of different inputs, and it doesn't have this like branching inside it. It's like naturally time invariant, right? But you're right that you could define hypothesis classes. What you could do is you could define hypothesis classes that like don't feel very time invariant. Is that Okay.
So somehow the architecture will.
Actually, yeah. But formally here, the thing is, okay, I'll get back to this question in a second. So, because you could define a non-time invariant and it has been done. Okay, so maybe this is, this is related. Let me actually, just to answer Rob, skip to the end here and then go back. So there's a similar process that was studied by, a very similar question studied by Eran Malach in a non-time invariant way. So also the question we're going to ask is, I give you a hypothesis class, I give you the base class of generators, and now tell me what is the complexity of learning this end-to-end. Okay? And the exact same question you can ask, but now when you do this, when you say that the way you're going to do this is at every step you're going to choose a different function from H. Okay? And that leads to very different answers. Okay? Because in this non-time invariant analysis, some of the complexity has to scale with the length of the chain, because you have to, at every step, you have to take pick a different setting of parameters. You have to learn all these parameters, and the whole point for us is we want to avoid this linear scaling with length, with the length of the thinking. We want to have complexities that don't depend or only a very weak dependence, maybe logarithmic dependence on the length and the time it takes you to think. Does that make sense? Okay, good.
Is the big T fixed? Is the time fixed?
So. Depends how you want to look at it. So I can define it, it's here it's defined for every t, right? The point is we want to get complexities that don't depend on t. Okay, so we want to get a complexity that only depends kind of on properties of H and not on t, and we'll see that in a second. Okay, so you can, but going back to here, you can think of two different learning models. One is in both cases you want to do the same thing. You want to learn how to answer questions. So you just care about the mapping from the input to the output. The question is, what training data do I have? So in end-to-end learning, all I have is examples of questions and answers. Okay, inputs and final outputs. And in chain of thought learning, I have M examples, but these M examples are of the entire thinking process. Okay, so I have much more kind of training data. I still just want to learn. What I care about is just getting the last thing, but I get much more training data. Okay, and that presumably can give you more data. So okay, so let's see how. Now the question again we ask is, I tell you something about the complexity of H, what's the complexity of these learning problems? So the simplest thing I can tell you is maybe that H is bounded cardinality. Okay? And bounded cardinality, also really all the classes we use as bounded cardinality, because if you use some class with d parameters, then you really only have something like something to the d parameters, so the log cardinality is roughly d. Okay? Because you represent your parameters with bits, and all our classes really are finite cardinality, and log cardinality scales the number of parameters. And the thing is that a very simple, I'm embarrassed to even call this an observation, is the cardinality of this end-to-end class, the number of end-to-end functions you can implement is bounded by the number of generators you can implement, because each generator implements just one of these end-to-end classes, right? And so we can immediately bound the complexity of the end-to-end class in terms of the complexity of the generator class. Okay, so in particular, if our class is based on d parameters, then the number of samples we need to learn this end-to-end thing is only scales with d, right, with the low cardinality, independent of the number of steps that we take. Okay, so this maybe answers some of the questions here, and this would not be the case without time invariance. Without time invariance, we had to learn H1 and H2 and H3, and we would get a scaling of number of parameters times t. Okay, that's clear. This is maybe this is the simplest and by far most important observation here. The time invariance allows you to avoid this dependence in t, which is, we'll see the whole point here. Okay. We can ask, by the way, what happens also with other complexity measures. So if you don't like discretizing things, you actually have some fantasies that you're using real numbers and not bits, and you want to bound things in terms of your generator class in terms of VC dimension, because somebody analyzed for you the VC dimension of transformers, or you're using some linear class that we'll see again and we'll analyze the VC dimension. Then you can then ask, okay, I know the VC dimension of the generator class, but that's not what I care about. What I care about is the complexity of the end-to-end class. So do I get the same type of dependence? I can bound the complexity of the end class in terms of the complexity of the generator class. It turns out the answer is actually kind of no. Okay, so you can, but with an additional factor of t. Okay, so even if the base class has VC dimension d, the end-to-end class can have VC dimension that does scale linearly with time. Okay, and so yeah, you can get a bound, but this is kind of a very disappointing bound, because our whole point was to avoid the scaling with t. So we already see here that things are kind of not so, are a bit trickier and not so obvious. By the way, already here, we do see a benefit for chain of thought learning, for learning with the entire data. So this is what the complexity. So if you're only learning with end-to-end examples, you'd need a number of examples that scales linearly. I mean, for some classes, number of examples that scale linearly with the thinking time. it turns out that with chain of thought learning, if you actually match the entire chain of thought, if you have access to the entire chain of thought, then you can, then now you do get, if the base class says recent dimension H, you do get a complexity that's almost independent of the type. Okay, and you can also ask, okay, if this is the case, like, is there something between cardinality and recent dimension? So, low cardinality is enough. Recent dimension is in some sense over here not enough. Is there something weaker than cardinality but can still be enough to bound independently or near independently of time? And the answer is yes. It turns out that the Lillestone dimension is enough. I'm not going to talk about it more here. If you're interested, I would suggest you read the paper. What I want to focus on here is not sample complexity but computational complexity, because that's really where we're going to see a huge difference between end-to-end learning and COT learning. I should say that from my perspective, I don't believe in real numbers. I mean, low cardinality is good enough for me. I mean, that's low cardinality is number of parameters, and that's good enough for me. Okay. Okay. So in terms of computational complexity, now we can ask, okay, how can I implement these learning rules? How can I mean, my learning rules here in the end-to-end is to find a generator that matches all my, end-to-end that's good fit, that matches all my my answers, and the COT, now I have all these intermediate steps, and I want to match all the intermediate steps. So it seems that that's actually harder, like it's more things to match, but it turns out that it's actually easier, because if I have the entire chain of thought, then all I have to do is match each step separately. And matching each step separately is just the same as matching what the generator will do. So I can reduce a problem of fitting this chain of thought data to a problem of just fitting data for the generator itself, to like ERM and generator. So in particular, if the generator class, I have an efficient algorithm for fitting it, I mean, it's easy to fit the generator class itself just as a purely supervised class thing of just the generator without any autoregressive or chain of thought or anything like that, then it's also easy to do chain of thought learning. So that's sort of computationally, that would also be computational practical. Formally, if the fitting is polytime, this is also polytime. The end-to-end, yes?
Maybe I didn't quite understand, but so we would end up comparing a case where you have the full trajectory observation, like length t,
right,
with like t times the observation of the last
No. So there's two different parameters here. M is the number of questions you have, and t is how much you think about each question. So in both cases, you have m questions, and each one of them you think for t steps. The question is, the difference is whether for each of those m questions, when you learn, like, okay, maybe I think, okay, and you're the learner, whether for each of these m questions, I just give you the question and the answer, or for these m questions, I give you the questions, the entire thought process of length t, and the answer.
But to make it fair for comparison, shouldn't we make the ones that gives one the answer, like t times answer, maybe run the question?
I don't know what fair is, right? I mean, so this is what I'm comparing here, right? I mean, you can say that I think what you're saying is that in some sense if I have the entire chain of thought, I have more more data. My hard drive is bigger, right? And what you want to compare is how much can I do with the same size of data file. Okay, you're right. So so in that case, so this is maybe why it's you're saying that here maybe it's not terribly surprising that you get a factor of t here. Okay, yeah. maybe. Okay, but when we got so let's set that aside, because I want to talk about the computational complexity, and here you'll see that this is not the issue, because my claim is for computational complexity. Even here you can do it in polynomial time once if you can implement the fit correctly. Then if you only have the end-to-end data, even though it's very easy to fit the generator class, the generator class is very simple, it could be computationally intractable to fit this end-to-end data. You cannot do it in polynomial time, so this is not an issue of having t times more time or data or whatever. Okay, you're just completely hosed. Okay, yes?
I thought this end-to-end fitting is something that people actually do, and
yeah, that's true. But that's true. We solve intractable problems all the time. And in fact, I think tomorrow you and others will probably tell us how to do that. But no, you're right. So this end-to-end, so what Nani is saying is that, again, let me just tell everybody to make sure everybody's on the same page, right? So what this is saying is that what really this helps me is just, if I just have the questions and answers, it's very difficult to fit, because I have to kind of guess what the thinking is in the middle, and that's very difficult. Okay, and there is indeed a lot of work now. I mean, I think the DeepSeek is usually attributed to the pioneering this, but I think it's also done before. And there's lots of work on exactly doing this and learning without the chain of thought, just with like using mostly RL techniques, right? And what this says is that this is in general intractable. This is a hard problem. Okay, the fact that we sometimes succeed, just there's something special that makes us succeed. And I think tomorrow there's going to be a lot of talks on doing that. So what you can view this as a base, is work kind of giving the foundations, explaining, giving, why in somehow fundamental way this is a worst case hard problem. Like something special has to happen. And I think there's a lot of very special, and we can talk about it tomorrow. Yeah.
My talk is not about this, but just
okay. But others I think tomorrow
will. I think of it as, if I want to do MLE, I basically need to integrate out the
so you can,
variables.
Right, you can think of it. You can think of it that way. So you have all this chain. There's a lot of latent variables, and you have to integrate them out, and that's like worst case intractable. Okay, and then you can think of all kinds of sampling techniques, but they're not guaranteed to always work. Okay, great. So how do it? Okay.
Is like the N, like the M that you talk, the question, or like when you say poly NT, like.
What is N? Where is N there? There's no N. N is M. That's a typo. Sorry. I have no idea what N is. N. Oh, I know what N is. What is N? Let's ignore that for now. I mean, I think I know what N is. It's because once you formalize things as polytime, you have like the index to problem complexity of how things scale. Like think of it as. Just ignore it for informally ignore it for now. Okay. Okay. So when I say it's hard, I mean in what cases it's hard. So it's hard. For some classes it's hard, and maybe the easiest class to describe it is the easiest class at all to study. Like when you want to study anything, always start with linear classes, linear regression. In this case, linear classification. So let's take our base class, the class of iterated, the class of linear threshold. So what I do each time, my tokens are it's a binary alphabet. The tokens are just bits, and each time so I have a linear function. So going back to Rob, this is a fixed linear function. I just like pad with zeros to if I don't have enough inputs. I apply the linear function to the suffix of my context so far, and I get it's a linear threshold. I get a new bit, and that's my new bit. That's the simplest thing possible. And again, in a realizable setting, this is easy to learn with perceptron or LP. It's an LP feasibility problem, or whatever else you like solving your classification problems. Okay, so the COT problem is easy. We also understand the sample complexity, but that's not what you want to focus about here. And the point is, what you can prove here is that the end-to-end problem is, even for this very simple class, is provably hard. Okay, you cannot. Subject to cryptographic assumptions about learning almost existence of one-way functions, or subject to some cryptographic assumptions, you can prove that it's you do not have any polytime algorithm that actually does this end-to-end task. So all these RN methods we'll hear about tomorrow are going to fail in the worst case. Okay. Okay. So now, how did all these hardness results? Oh, and I should say that. I also want to, maybe I should have, sorry, okay. I also want to point out that here also, this class, and again, going back to the work by Malach that I mentioned, so how does this hardness result work? So all these hardness results, the way they work, like to prove that something is hard, I have to show you that this class is very powerful. So in particular, what is powerful, I can show you how to embed any bounded depth circuit as a linear threshold. So for any bounded depth circuit, I can actually give you a linear predictor so that iterating this linear predictor computes the bounded depth circuit. Okay? And so if you could learn iterated linear predictors, you can learn bounded length circuits, and that's a very powerful class that is not learnable under standard cryptographic assumptions. Okay, so when I tell you a result like this, then you can think, well, okay, this I'm phrasing as a negative result, but maybe it's actually a positive result, because I just told you that even the linear thresholds are actually very powerful. They can implement any bounded depth circuit efficiently. Okay, so maybe we should actually think of this as a positive result. But then you can say, well, do I, how strong is it? Well, I can only handle bounded depth circuits. And also, if the dependence here, L is the depth of the circuit, you can see that the length of the linear predictor that I need, like the dimensionality of the linear predictor I need, scales exponentially with this depth of the circuit. That's why I can only handle bounded depth circuit. So it's actually a very weak kind of simulation result, if you want to think of a simulation result. It's enough to get the hardness result, but it's kind of weak as a positive result. And you can think, oh, maybe I can strengthen it. Okay, maybe. Actually, I don't know. Maybe you could. Okay, but I would argue this is a losing game. Okay, you don't need to strengthen it because this is kind of not what we want. In fact, if what you wanted to learn is circuits, there's a much more direct way. Then you would go to Eran Malach's result, which looked at a non-time invariant version of this, which at each step used a different linear transformation. Then you can implement any circuit of any depth, and the number of parameters you need corresponds to basically the size of the circuit. Like it's going to be linear in the size of the circuit. You can do it a bit tighter than Eran's construction. Okay, and the main reason here is that what's going on here is that circuits are inherently kind of non-time invariant. They're not. There's no time, but they're not like homogeneous. They're not like uniform. Every gate really does something very different. There's nothing kind of recurring there. And so this is exactly not what we want to capture with these like time-invariant autoregressive processes. What we want to focus about is actually things that are not circuits, that are actually, kind of have this more time-invariant. So what I have to tell you is a bit of my deepest fantasies here, okay? And this is really what I want to learn. I'm serious. I mean, this is kind of how I approach machine learning. So what really I would like to learn? So ultimately, what I'd like to learn, anything that's describable, I'd like to learn, okay? Anything, and this is a very broad class. But the thing is that it's actually learnable because anything you can write any type of description for it that, with S, bits, characters, whatever, then the log cardinality is only S. I only need like S data to learn it. Okay, so this is very powerful, in particular when you think of describing things. Even though you can learn anything that's describable, more usefully you would talk about programs, because like if you can, really what I want is to automate things, so instead of like I want to learn instead of to design or program. And if some function like can be described but can't be actually implemented, who cares about learning it anyway? So I just want to compete with programs, which is a certain type of description, right? So anything that Kevin here is an expert programmer can program, I don't need to program, okay? I don't need, because I can just learn it, and the amount of data I need to learn it just is linear in the length of Kevin's program, okay? So that's a very strong result, okay? So the only problem with that, the reason learning doesn't stop here, it really would if we only cared about statistics. The only problem is this is not computationally tractable. I can't, like when I say I can learn by enumerating over all programs, over M. That's not even computable. Okay, even if I limit them somehow, maybe it's like a bit computable, but it's not tractable. Okay, and so this is kind of not like I want to get something that I can learn and is tractable. And note that here also, though, the output wouldn't be tractable because maybe Kevin can write a very short program, but it takes like triple exponential time, and so that's not going to be, there's no point in learning that anyway, because even if I succeeded in learning, I'm not going to be implemented. So what I can compromise is learning things not just that have a short program, but then run in a small amount of time. So now the game is as follows. If Kevin can write something that runs in time t, okay, then I can learn it. Well, I can learn it in time that's proportional to its length of the program. Definitely, I can write and learn it in time that's proportional to the length, the runtime of the program. Okay, so the advantages now we're in much better complexity-wise because this problem is actually NP hard. Okay, sorry, it's NP complete. And NP complete is good news because in particular it means that it's NP. Okay, so if P equals to NP, this I can actually do. Okay, so this is good. If P is not equals to NP, well, I'm still a bit in problem, but not all is lost because the thing is that anything I can compute in time t, I can also implement in a circuit of size t, which means I can implement with a neural net of size t. And so if I'm learning a neural net, feed for a neural net, really what I'm doing is I'm learning all the functions, learning it of size t. What I'm doing is I'm just learning all the functions learnable with time roughly t. Okay? And this is, I really believe, this is the real reason neural nets are so great because they're universal. It's a way of learning anything, anything that's doable in time t. In a way, okay, of course I can do it in the worst case, but at least I can try. Like enumerating over over programs is like a lost cause because it's non-differentiable. This is at least differentiable. Okay, and again, I think this is like supported also by history. I will take, even though a minute of the time I don't have. I think the history here, and you're going to have to explain to you. I have these pictures before. So why am I putting Shannon here? I mean, I hope everybody recognizes this is Shannon. Why am I putting Shannon in this context? What does he have to do with this? What was? Nobody? It's not communication. Okay, so Shannon's master thesis, okay, essentially told us that anything that I can implement, any function I want to compute, I can implement with a circuit. okay, which is not that different from a neural net. Okay, a few years later, McCollum and Pitts, who were well aware of Shannon's work, thought about instead of electronically feasible models of computation, of biologically feasible models of computation, and wrote a beautiful logic paper introducing neural net. And again, neural net was introduced very explicitly as a model of computation, saying, look, anything we can compute, okay, we can compute with a neural net, with a very close definition of what we have now. So neural nets really, their whole basis is as models of computation. Okay, the only problem with these, both of these were discrete models of computation. And Werbus pointed out that like we abandoned McCollum and Pitts because they're discrete. We can't optimize them. Okay, and then of course the solution to that is to make them continuous. Okay, and once we make them continuous, we can just use gradient descent, and this is what we're doing now. Okay, so this is really, I think, the correct historical view of neural nets. Okay, so good. So this is fine, but now the problem is that note that with this, the sample complexity that we have has to scale with a runtime. But in principle, the sample complexity doesn't have to scale with runtime. It has to scale with the length of the program. And the length of the program can be much, much, much shorter than runtime. I mean, Kevin can write programs that are very short, but run in much longer time. And we say, okay, we don't want it to run in triple exponential time. That's fine. But if Kevin writes a program that's like, like 150 characters and runs in time that's like, n squared, where the n is input length, okay? Why should my learning time for it scale as n squared and not constant? Like, why should it depend on the runtime? Okay, so really what we should ask is this class of programs that are both short and run in small amount of time. And what we can hope is to learn with the runtime complexity might depend on the runtime of the program because we have to try it out or something. But the sample complexity should still in principle depend only on the program length. Okay, so how can we do that? And so this is really what I'd like to learn. And my claim is that's something we can do with this time invariant models. Like this is really should be our goal. Oh my God, this should be our goal with autoregressive models, because with autoregressive models, the point we saw is we can have things that their sample complexity is independent of the number of computational steps, the time it takes them to think. Okay, so our goal here is to construct a simple generator class, okay, that can actually learn any program that is of length s and runs in length s and time t in sample complexity that depends mostly on s and not on t. Okay. So we can think of our linear class, go through this quickly. I can tell a linear class, the simple linear class are a solution to many things, but here it's not a solution. They're not powerful enough. You can easily prove it. But is there a different class? Let me skip that and just ask, is there a different class? So this is our goal here. Can we design a generator class that has, I wanted to have three things. First of all, I wanted that if I take this generator class and I do autoregression or chain of thought for t steps, it can simulate any program that can run in time t. So the complexity of the class has to scale with s, and just the number of iterations has to scale with t. Okay, maybe up to log factors I'm going to allow you. You'll see later I'm not going to need them. Okay, and I need it so it's easy to fit this generator class. So this generator class is the fitting. Just the generator class itself is easy, and then I know that it's easy also to fit this chain of thought. And then I can actually tractably learn any program that runs in time t and is of length s and number of samples that only depends on the linear in the program length. Okay, and this is possible. So it's not too difficult to see this is possible, at least with a synthetic generator class. In this generator class, what we'll do, basically we'll use our chain of thought to simulate a Turing machine. So each each token of the chain of thought would encode a step of computation of the Turing machine, like what state we're in, where is the what's the current state of the machine, what's the current token on the tape, and are we moving right or left? Okay, and the generator class would be basically for each Turing machine, I can define a generator, and this generator just takes all this history of the computation so far. In its head, it can simulate the Turing machine, and now it can open the next step of computation. So all it does is simulating Turing machine. There's a one-to-one correspondence between Turing machines of size s and this generator class. Okay, let me just write down explicitly this generator class. Again, so what it does is the class formally is just a mapping from a sequence of tokens to the next token, right? So it has to take the sequence of tokens describes the computation. And now to do the next step of computation, you have to figure two things. First of all, you have to figure where you are in the tape, because the tokens only tell you where you are at move or right. So that's easy. You just sum up all the moves and you know where you are in the tape. Okay? And then you have to figure out what's actually written in the tape there. So to see what's written in the tape, you have to go to the last step in the computation that wrote somewhere in that position and figure out what they wrote. Okay, so that's what you do here. Okay? You find the last time I wrote to my current position, and now I know the tape symbol, I know my state, and I can execute the next step of the Turing machine. Okay, why am I? Okay, so first of all, my claim is this satisfy my Desideratum. I mean, I can easily. This is kind of so trivial. I'm just going to skip it. I can easily see that this actually is of the right complexity. It only as large as Turing machines. It's very easy to fit, and it can simulate everything. It's exactly what I want. But what I want to emphasize, what I want to look at a bit is look at this, and let's look at this. And what I described here, how can I implement this? This is, for those of you who are familiar with attention, which I hope is everybody, this is basically, attention is exactly what I need here. Because what's going on here, this lookup and everything, these are all like local operations. The only thing here that I have to look at other tokens, the main thing is this operation that I have to find the last place that I wrote in the same position I currently have. And that's exactly an attention operation. I'm using as keys all the positions that I wrote, as a query the position I want to read, and as values what I'm writing. Okay? So informally, that's maybe hard attention. There's also maybe a slight use of attention here to calculate the position. Maybe I need uniform attention. And again, this is a discrete. Here I write as a hard, so discrete attention. But now we're going to do this moving from McCollum-Pitts to Hinton and making this continuous rather than see here I made it continuous rather than discrete, so I can take gradients. I mean, but this is all like kind of details that are not so interesting. If you want to hear more about these details of what making, once you make things continuous, like it's a mess to make things continuous, and then you have to like worry about much more. And then a bunch of like authors that worried about all these details and showed how to do this also with continuous attention. Okay, so great. So now we see that what we did is we moved from Turing and McCollum-Pitts, which is a non-uniform model, like circuits, okay? And then we can only learn with time. We really have to pay attention to the time, to Turing, right? And the main idea of Turing is that now we have a uniform model. We only care about the length of the program, the length of the machine, and not like the time of computation. And so this, so far I didn't do anything new. I just maybe gave a new view on something existing. I'm just doing like chain of thought with transformers, okay? But now you can ask maybe the following question. What about the length, the context length, the length of the tape? Okay, so that's kind of our memory. But note that even if Kevin's program that he wrote so diligently is very memory efficient, uses a small amount of memory, the length of the context that I'm going to need, the context is going to grow linearly with the time, because every time I think, I have to write. My only way of thinking is writing. Okay, I have to write as I think. And so I'm going to need context length is not going to scale in memory. A natural question to ask is, can I save on that? So in particular, if I have, if I actually want to compete with a program that Kevin wrote that is of length s, so I want sample complexity s, and runs in time t, and uses only m memory, can I do that with context length that somehow depends only on m and not on t? Okay, so with standard chain of thought, I cannot. Okay, but once you think of it this way, it directly motivates how to do it. Because when you think, okay, you don't think like a Turing machine. Okay, or when you program, you don't program a Turing machine. I hope. Okay, and probably most of you don't program a 1954 Fortran. Okay, so 1954 Fortran really kind of operated this way. And the big invention that came in 1950. Around that time, okay, it was incorporated in 1959 Fortran, I think, was the stack. Okay, so what's the idea of the stack? So this is was Klaus Samuelsson that was before that basically invented the stack. So what's the idea of the stack, right? You write things in the stack as you're computing, but then you clear the stack. You write and then you remove things, right? So you can do a lot of intermediate computations. You can call a subroutine, but when you're done with it, you can forget about all the memory for the subroutine. And this is really how you work also. When you think of something, but then when you're done thinking about it, you can erase the board. You can do a lot of thinking with a very small board. You think, and then you erase. And then you think, and then you erase. You just keep your final result, not the intermediate computations. So what you can do is we can very easily modify the autoregressive chain of thought generation to support that. And we do that by introducing 3 special tokens, okay, which we're going to call, separate, and return. Okay, and what happens is these are just 3 tokens you can emit, but every time you see this pattern, okay, so every time when you do the auto generation, we see this pattern. In particular, every time we emit and return, then we remove everything between the call and the separate. Okay, so you can think of this as T as the intermediate computation of the program, of the routine, and A is your answer. Okay, so in particular, we have this as standard autoregression, but now we have also an additional. We do, instead of just generate append, we do generate append reduce, generate append reduce, generate append reduce. The reduce step, like if there's no return, does nothing. If there is a return, it finds the preceding separate and call and like erases the middle. Okay, so this is why we call it pencil, because you can not only write the pencil, it can also has an eraser. You can also erase the stuff in the middle. Okay, let me skip this example. I solving some constraint satisfaction problem here. I try something, I call, whatever. Whenever I return, what I do is I cut this out of the context, right? So and then I can continue on even time it could return. So maybe it'll be clearer from here. Oh, where is it here? This is kind of what I did with standard chain of thought. It'll be very long, but with pencil, my chain of thought, the overall number of tokens I emitted is the same, but it never gets long. Okay, so this is an example for chain of thought. Another example, I'm just putting it to make Zaid happier so that he doesn't cut me off, is Einstein puzzles that some of you might be familiar with. And again, basically it's a natural language problem, constraint satisfaction problem. I have to check all kinds of settings, but once I'm done checking, I can like remove all my intermediate calculations, use my pencil. Okay, and the thing is that using this, I can very significantly reduce the chain of thought, like by huge factors. Okay. And this allows me to, let me skip the theoretical result here and jump just to the experiments. And this indeed, I can do things a bit faster also because I save on tokens, but the main thing here is I can get good accuracy for much larger problems. So this is a comparison of using standard chain of thought and pencil. And you can see that with pencil, I can, with standard chain of thought, accuracy starts dropping once the problem gets a bit too large. But with pencil, I can continue going until very large problems. And again, also in Einstein puzzles, I can handle problems that are, with fairly small models, problems that are much, much larger. So here you're seeing, this is for small problems. So for small problems, I can handle also with the with standard chain of thought, but the main effect is the size of the model, the size of the context. I can make things with much, much smaller. Okay, let me just finish here without asking all these amazing open questions you can ask me about later. And just summarize what we had here. So what we saw is, again, a theoretical work of like trying to really lay the basis to autoregression so we can exactly ask all these questions that Nang was asking about, like to show, to establish end-to-end is hard in general, and now you can give me all kinds of conditions under which it's easy. Like if I do have maybe, and you can ask, this is some of the question I skipped, you can ask lots of interesting questions now in a theoretical way. What about, for example, if I have lots of end-to-end supervision and a small amount of chain of thought supervision? Is that easy or hard? What about if I have statistical information about the chain of thought, because through pre-training, does that make it easy? Okay, you can now ask this in a formal way. So this provides you a firm theoretical foundation. And also we can, using this, we can understand now transformers and autoregressive generation through this lens of computational models, which I'd strongly argue is absolutely the right way to think about these things. And once we think in terms of computational models, it directly motivates augmenting them with this eraser mechanism that allows us to also empirically solve natural problems much better. I'm way over time, so let me end here. Sorry, Zaid. Thanks.
One question.
We had many questions before, so I don't feel so bad. But like, yeah, one hard question. Nobody wants. We have 2 questions. Nobody wants to ask to be the single person to ask a question. It's fine. Yes.
I mean, I was just thinking about, like, we talk about using RL versus the hardness result here. I guess the RL view, which is related to your open question of thinking about different kinds of data and so on, right? So I guess the success explained by RL is that if you think about learning from scratch and you don't have the COT data, getting those intermediate tokens correct is almost impossible. Right. But in reality, we have pre-training.
Right.
Like originally actually initialize RL with good coverage
Right, exactly.
over like what's plausible things to say in the middle. That helps.
Exactly.
It's like RL is really just doing the final bit of fine tuning. You rely heavily on
Exactly. Exactly. So you can formalize it in this model exactly as you said. Like you said, I don't have exact COT data, but I have I have end-to-end data, exact end-to-end data, and statistical COT data, for example. Like, and now I can exactly formalize it and ask, is it easy or hard, and get like measures of coverage. And I think, again, maybe you're working, I think Dylan will be speaking about this tomorrow. But yeah, I think others, maybe I don't remember the entire lineup for tomorrow, but I think, yeah.
So you talked about how you make this differentiable version of things, which is attention.
Right.
And so how is this generate, append, reduce? Is that a trainable
So okay,
feature?
it's completely okay. So the thing is that the reduction step. So this is actually important. Maybe I understand. The thing is that the pencil is completely orthogonal. And I think I had a slide that I skipped here, but okay. So pencil is completely orthogonal to the generator class. So I take a generator class, and any generator class I can put pencil on top of. Pencil is discrete. Pencil is not continuous. Okay, but it doesn't have to be. If my generator class is continuous, okay, then I can define the loss that I didn't. It's not in these slides, but the loss is basically just the fitting loss for fitting when I apply these generator steps. When I apply, these reduced steps, and that's going to be continuous. So this is the pencil has nothing to do with transformers. In the sense, I could put pencil on top of transformers. I could put pencil on top of RNNs. I can put transformers on top of decision trees generating the next way. Any generator class, I can take it and put pencil above it. And I can define the loss, which I'm not going to, it's a hidden slide that I removed. I can define the loss, the appropriate loss, and if the generator class is differentiable, just as a generator class on its own, then the loss when applying pencil would also be differentiable. Does that make sense?
I'll have to look at the
Yeah.
paper, I guess, with more details. Yeah. I think,
Maybe, yeah. Okay. I can show you later, but yeah.